statistics. This week we are going to do a little bit more work with normal curves, and then you're going to start to learn about sampling distributions. I haven't heard from anyone in the past week about the new material that I sent, so I'm going to assume that you understand it. So let's start with this notes page. A little bit of a review. The formula for a z-score is z equals x minus mu divided by sigma. And last week you were using z-scores to find the area between scores on the normal curve, or the area to the left of a score, or something like that. This week you're going to be doing some similar stuff on your practice page, and I'll get to that in a second. But first I want to talk about how to tell whether or not data have a normal distribution. So there are a few different things that you need to look at. The first thing is a histogram of the data. In order for data to be normally distributed, you want a histogram that is roughly bell-shaped, or we've called it mound-shaped in the past, and you want it to also be symmetric. So sometimes you'll be given a histogram to look at, other times you may have to create your own histogram. The second thing you want to look at is outliers. And you'll remember our formulas for outliers. First, you have to find the IQR, which is Q3 minus Q1. And then you need to do Q3 plus 1.5 times the IQR and Q1 minus 1.5 times the IQR. And remember, this gives you your fences. Anything outside of those fences is going to be an outlier. If a distribution has outliers, that is starting to point to the fact that it may not be normally distributed. The third thing that you want to look at is skewness. So we know that normal distributions are symmetrical. If you see your histogram is skewed to the left or skewed to the right, that would be evidence where you're starting to say, okay, this is not normally distributed. Another way to measure skewness is this thing called Pearson's index. And the formula for Pearson's index is 3 times the sample mean minus the median divided by the sample standard deviation. If you get an index value greater than 1 or less than -1, that's an indication of skewness. And again, if your distribution is skewed, then you can't necessarily say that it's normal. The fourth thing to look at is a normal quantile plot, or you could call it a normal probability plot. This is something that gets created using like statistical software. I don't think that you can do it on your calculators. If I ever want you to look at a normal quantile plot, I will give it to you. But what you want to be looking for in the normal quantile plot is that the points on it, so it sort of looks like a scatter plot, the points on it should be close to a straight line. If those points are close to a straight line, then you can say that your data is probably normally distributed. If you look at the points and they're way far away from being a straight line, then that's evidence to suggest that your distribution is not normally shaped. When you're looking at these 4 things, any one of them might provide some evidence that your distribution is not normal, but you really don't want to draw that conclusion until you have evidence from probably more than one of these. So in looking at all 4, you're trying to gather this body of evidence that says whether or not your distribution is normal. So let's talk about some of the other things you're going to be doing on your practice sheet this week. Basically, these 4 things are the 4 types of things you'll be doing. You'll want to be finding probabilities if a z-score is known. That's It's very similar to what you were doing last week. Area to the left or area between two things. And on the input in your calculator, you can do this using your calculator. Notice you've got lower limit and upper limit. If you're looking for the probability that a value is between two z-scores, you're going to plug in the lesser one for the lower and the greater one for the upper. If you're looking for, say, the area to the left, then your lower, you want to use something like negative 9999999. Just put a bunch of nines in there. And then your upper is going to be whatever that z-score was. If you're looking for area to the right, your lower bound is going to be that z-score value, and your upper bound is going to be like 99999, however many. Because here what you're saying is you know that the asymptotes of the normal curve go out forever to the left and to the right. But if you're plugging in a lower bound, say, of negative 9999999, any area that's further to the left of that is going to be so minimal that it's not going to make a difference in your final answer. So that's why I'm using these bounds. Okay, the other thing you're going to need to do is to find a probability if you know x values, the mean and the standard deviation. So this is, you know you have a normal curve instead of the standard normal curve. And maybe you know the mean of that curve is 70, and you know the standard deviation is 10. So here's a rough sketch of that curve. Let's say you want to find a probability that one of your raw scores is between 65 and 75. Then what you're going to do is you're going to plug in your lower limit, that would be your 65. Your upper limit would be 75. The mean was 70, and the standard deviation was 10. So you're going to plug those values in and then find the resulting probability. And again, notice I made this point here. If you're looking for area to the right, that would be x is greater than some number, you're going to use an upper limit of 9999999. If you're looking for area to the left, you're going to use the lower limit of negative 9999999. So for both of these on a TI calculator, you're going to get to this menu by doing second vars. So this is the same place we went for binomial probabilities. Second vars, and then you'll see there's normal PDF and normal CDF. You're always going to be using normal CDF. That's the one that you want. In the example I just gave, my lower bound was 65, my upper bound was 75, my mean was 70, and my standard deviation was 10. I'm going to hit enter, and for anyone who has an older calculator, like Haley, I know you have an older calculator, this is how you're going to plug it in here. So you'll get the normal CDF up on your home screen when you press it, and then you're going to do 65, 75, 70, 10, and hit enter. And we're getting that area of 38.3%. So that's the probability that one of your raw scores is going to be between 65 and 75. Okay. The third type of problem that we're going to see is the reverse of what you've just done. So let's say I give you a probability and I want to know what z-score that came from. Let's say I know that there's some z-score that the area to the left of that score, let's put it here, the area to the left of this score is, I don't know, 0.23. I'm going to go to my calculator and I'm going to do second vars, and notice inverse normal is number 3. And the area that I said was 0.23. In this case, I'm talking about z-scores. So I'm talking about the standard normal curve, which has a mean of 0 and a standard deviation of 1. I'm going to hit enter. So again, this is what your input would look like if you're working with an older model calculator, TI calculator. I'm going to hit enter, and I get that that z value was negative 0.739. So that's what my z is. I can also do this to find raw scores. So that's the last one here. So let's say I'm going back to my normal curve that had a standard that had a mean of 70 and a standard deviation of 10. And I want to find the raw score that relates to an area under that curve of 0.23. So I'm going to go to my calculator. I'm going to do second vars, number 3. I still want it to be 0.23, but now my mean is 70 and my standard deviation is 10. I'm going to hit enter, and I see I get a score of 62.6. So that score that has an area of 0.23 to the left of it is 62.6. These are the types of problems you're going to be completing on that practice sheet, which is what you should do next. When you've finished with that, check your answers on Moodle, then you'll need to go on to the activity about sampling distributions. And please, let me know if you have questions.